talk to us. You got 11 minutes for your presentation. After 11 minutes, you're going to get penalized and so forth. My name is Nick Zorka. We're going to be your judges for today.
We'll be introducing ourselves.
Pardon?
I said we'll be introducing ourselves in minutes.
Good, good. Are there any questions?
No.
Whenever you're ready to go, let me know. I'll start.
Morning, my name is James Delpon. This is Michael McGinnis and Kat Fraser, and we're here from the University of Massachusetts to tell you about our robot Start. So, Start is a four-wheel drive tank steer robot, meaning it can turn within its own frame size. To do that, it has a gear system like this. This is set up on both sides. So each motor is run on each of those idler pulleys, which is run by the motor which is up here. And there's two idler barrels that allow us to tension to get maximum chain wrap around those. As you can see right here, it's made completely out of aluminum. It's been milled out to lower the weight. The weight went from about 350 pounds down to 250 pounds by milling out all of that. It's split into three sections, which is the electronics case, the mast, and the chassis. The mast houses all of our sensors, the electronics case houses the computer, motor control, and stuff like that, and the bottom houses the batteries and motors. To power a robot, we use two 12-volt SLA batteries, which are used to give us the sensors don't like that, so we give it, we have a 24 to 24 DC converter to power the SIG, so that it has a nice power supply. We have a 24 to 12-volt DC converter that gives us 12 volts for a computer system, and then all of the other sensors are powered through that. In addition to that 12-volt system, there is a smart car power supply, which will shut down the computer smoothly. It guarantees 90% to 95% efficiency, and is also fused to make sure that the computer doesn't fry. All of that is run through a single fuse block, which every system is on its own fuse. So if anything does blow, it's easy to change with the back up. For a safety system, the competition does require that you have a wireless and physical e-stop. So to do that, we have two e-stops, one mounted on the rear of the robot, one mounted on the front. This way, from anywhere on the robot around it, you can easily hit a button should there be anything wrong. As for wireless, we are implementing a 900 megahertz Zigbee-based radio. So that allows us to do two things. We can have heartbeat. So instead of just pressing the kill switch and the robot shutting down, if the robot goes out of range of the remote, or if the remote ends up dying, the robot will not see the signal anymore and shut down. It also allows us to get feedback. So I can press the remote e-stop kill switch. The LED on the remote will turn blue from green. Once the robot says yes, I'm an e-stop, it'll then turn red, and you'll know that the robot is e-stopped from wherever you are. As for range, here we have been able to e-stop the robot from across the street over at the hardware store. So our range is much higher than a lot of the previous e-stops that we used. For sensors, they're in two separate categories. The first one's obstacle protection. For that, we are using the SIG LiDAR, which is giving us the map of where everything is in front of us. And we have the cameras, which we're using to detect white features. The sawhorses are white, the lines are white, there's white stripes on the barrels, so that can be used for obstacle detection as well. The other would be localization. We're using 2 off-the-shelf USB GDSs. Ocean Server Compass, which is also giving us yaw pitch. And 2 digital encoders on motors, which are 512 clicks per rotation, and so we're getting very high accuracy on it. So to talk about our software architecture.
So before I go into the actual software architecture, I'd like to note that we're using ROS, which is a robot operating system, which is sort of a meta operating system that our district on top of Linux. This gives us our great message passing facilities. So we have a many-to-many model for publishing and subscribing to just generic message racing relationship data, things like LiDAR and maps and things like that. We also have package management. That there's a lot of pre-built packages for us that we can deal with, and also we can make our stuff in packages that has proper requirements and dependency management as dependencies and so forth. We get our hardware extraction layer that previous iterations of our team, we usually use like a player stage system. So the similar thing here where we can run pretty much the same code in simulation and on the real estate mod and not have to worry about the hardware as the software doing. And finally, one of the key features of ROS that we're definitely trying to leverage this year is the idea of a transform tree. And that is that we build a tree of physical transformations between different frames related to the robot. So things like where the laser scanner is, where the center of the robot is, where the camera might be pointing, and also where we might be anchoring maps that we're building. And so we can publish the individual links of this transform. And then ROS provides a utility for simply listening to all these different published links. And we can ask, where does this message look like if it was in this frame instead of the frame we have it now? And that automates a lot of annoying trait that can often lead to hours of annoying software, like debugging of maybe putting like sign in the wrong place, or should be a negative sign in. So this is a general overview of the software system. So the green here is really the physical sensors that Jim already talked about. So we have a closed common filter that integrates the encoders, the compass, which has it's really it has acceleration of it as well. 2 GPSs, and then we also have the laser and camera. And the end goal of the system as we go through, so the vision system, which Ken's going to talk about in a moment, and then this laser mapper here, is we're going to build 2 occupancy grid style maps with the laser scanner and then a simulated laser scanner based off of analysis of the camera images. And then we're going to merge those together into a single occupancy grid based map and do path pointing on it. And then we're going to use both the map and the laser scanner to do path following on the path that we just generated. We'll try to carry that out. And just get to talk about the vision component.
And vision for the robot this year. We're using vision to set white features on the fields, painted lines, certain angles, like soft blues. So the way we're doing vision this year is we're taking an image, we're doing a mean chip filter on it. After that, we fix the color channels. It's pretty much just different color channels as we apply our lens. It's a nice black and white image. After that, we just do a little bit of shielding and put a little transform, and we get really nice lines. After we get a segmented image, we do a bird's eye perspective transform. We get a top-down view of the fields in front of our lot, and we run a raycaster. You can see this checkerboard was warped back from the projected view to after we have the projected view, we do a laser raycast to simulate a laser ray scan like this thing. This gives us 180 points in front of the robot and height space. We get a good distance off that because we're straight up fake a laser. After that, we convert to 2 way scan passes. Like what this says, we have a place that it's great.
I'm going to talk about further up the navigation stack. So, as I said before, we're mapping an occupancy grid. Basically, that means we're casting our rays onto an occupancy grid to where they have like hits on the map, and then we inflate those obstacles to approximately the size of the robot, which simplifies path planning because we don't have to consider the robot to have any sides when we do the searches. And so then the two maps are merged together using a very simple concept of the laser and the camera see mutually exclusive types of obstacles for the most part. So they should find and clear their own obstacles, and then we can simply take the worst case of every cell in the map. And if the laser thinks there's something there, laser and the camera does not, then there probably is something there that the camera might not see. So we just take the worst case of every cell. And then once on the map, we do theta star, which is a modification of A star that basically allows you to get any angle between two cells when you're doing map search to generate a path. And then we do path following with a technique called WOW, which I believe we talked about years past that we developed after doing competition here. It's basically a reactive obstacle avoidance. We do that using a merge of the laser scan from the actual SIG LiDAR and a projected laser on the camera-based vision map so that we can not drive over the lines even if the pathfinders aren't too close to them. And we're actually going to show a video of the simulation environment. This is the visualization of the environment. So essentially just placed a waypoint right here. You can see this green line is the path that's being produced. And the black is something that's considered an obstacle on the merge map. There's the lighter color here is something that's considered clear. And the two lines coming out of the robot are involved with flow, which is the obstacle avoidance. They're basically describing the lane that the robot is taking.
So our robot has a top speed of 5 miles per hour. It weighs about 280 pounds.
Talk about the cost.
So the goal for this robot was to cost as little as possible.
The drivetrain
Obviously, there are some things that do cost more than some of the sensors. The SIG cost $4,000, $5,000. So what we have here is the cost breakdown from the aluminum frame all the way down to the electronics. The end cost was $9,400 for the current configuration. It has been updated since a lot of that was donated, but we kept the cost of each one of those parts in mind. This cost does not include machine. I do realize that there is a lot of machines on these cars, but without getting a quote from a real machine
So this
shop
year,
inspector.
our weather survey is canvas. Spread this with a
Quick to make our sponsors, give us a offer. Cost of your best part is 6.
We have fan covers. We have the airflow system.
You were a minute and
So we
55 seconds.
design these fan covers to keep the rain out. And the covers also have filters.
Can you go back to your simulation video? And I couldn't hear. What was black? What was white?
The black is something that's considered an obstacle. That's an obstacle.
The black is after.
Yes, on the occupancy grid. And the almost white gray is considered blue.
It's designed through
And so how do you get around the obstacle there? In other words,
design analysis.
Yeah, how do we generate that green path?
Yeah.
So that's an algorithm called theta star is doing that, which is just it's a search algorithm. It's a variant of A star. Basically, it's A star except you keep doing line of sight checks when you do additional node searches, so that you can make it like any angle as opposed to A star, which you end up getting this awful like grid behavior where you're only allowed to do grid neighbors. It's very blocky. So this is just a modification that allows much smoother angles.
which sensor takes precedence? Which sensor takes precedence?
Neither. We trust both. So we take the worst case in every grid cell. If anybody thinks it's occupied, it's occupied.
What do you do then?
Why? Oh, what do you? Well, then, what do you like? Then that cell becomes occupied on that becomes searched.
So then you make a movement based on the fact that there's something offended.
change the search path, and then that will change what the obstacle, where the obstacle point is trying to travel to.
So we built up a map where we know things are or aren't. So if we get to a point where we are stuck, it will know that it can turn back.
It's constantly replaying, so we'll replay our obstacle point here.
We also talked about dual GPS
We still don't have any real data on how much that helps us, but we're still doing it because it seems to be better than one GPS would be.
So, we actually have tested it on the field where we robots and lost accuracy and thought it was within 300 of where we tested it last year.
How much software architecture utilize a lot of these features that you see there, EKF or
No, we're using a different software library for EKF. I didn't do EKF myself.
So, yeah, I'm using, what is it? I think I'm using K-Filter, which is a C++ common filter library. Yeah.
Wow. The Ross one just not as well.
I had trouble with whatever Ross had at the time, and the K-Filter was just really simple.
Part of the problem is that the ROS navigation stack, which a lot of that stuff is really heavily built into, really is not designed for a type of application we have. Mutually exclusive sensors. Yeah. There's really no way to put that in that ROS navigation stack at all right now, which is why we put it around.
King of influencers. He's better. I just have absolutely no idea how much better.
This whole part.
No, sit over there. That's what it's also the privilege that sound like everything. That might be true.
It is slightly shaky, but the refresh rate is such that it doesn't. We enjoy trying to use the constant sensors. They do have a microphone array. Do you have any issues with that sensor?
We designed
That's the receiver for our install. So this is a kind of receiver. that's all we're using.
I was gonna say, if you drive something,
So there is over here. So you can modify the temperature. 2 Allen screws. Either Allen's or and they are spaces storage is the line of loosening that zone trains. So you can just crank one. So the encoder should those were something. They are inside. So you have any issues with your encoder running correctly? You have any issues at all with error associated with that? You have it because there's no visibility as well as putting it on
Hello everybody, good morning. Just wanted to make an announcement that the JAWS competition will be open at 1:30. JAWS competition is located at the north side of the field, right behind the running backs. So if you guys want to go over, leave your boxes and actually go over there. But also we have
So we can also use the system of removing those vertical. Ross does use to turn angles and links to turn that's mostly the purpose of that. You get so for instance,
So I think
we get these laser that are either the frame that is set on the laser but we want to better map. So we have a map frame that's based off of some GPS sure, yeah. And I can go, hey Ross, reach this on the map frame and it will automatically whatever. Sure, you don't have to worry about that transformation. Yeah, no.
everything about this was even like the batteries and models is so small.
So you ran stress.
So according to Academy post on paper that said that all GPSs will have the same thing. In practice, it doesn't turn out to be that way, so all one is but if it's two separate manufacturers have two separate, they have different antennas. So the same manufacturer was theoretically. But if both of them are running off into the same direction,
How much is the big one?
it's very expensive. These two are actually shaped out in this national soil refreshment program, and it's running along the inside some of the IGVC. A few things that we didn't talk about, such as the front markers, so where it's inside, that's when it starts motion. And that's her. What we're using temperature is right now that is a big problem. We do have
Anthony, you want to grab Jim?